Hello mate and welcome back to Let's Code Season 6. As promised, we are going to spend a little bit of time working through the pathfinding algorithm. Now I know that we've already covered this, but there are some minor changes that we need to make it useful for our program or our game. And there's also a couple of things that I wanted to talk about. The first one is that if you look at the top of this file, you will notice that there is no init Python statement. And that is because I have moved this Python content, this Python code, into a Python file. As you can see, I've called it gdt.py, but you can call it whatever you want as long as it ends with .py to signify that it's a Python file. And where you're going to need to save this is directly into your game folder, not in any subfolders, just in the game folder. And then we can actually utilize this by saying, in this case, because our method or our function is called a star, we can just call a gdt.a*, or whatever you call your file. If you call your file Dave, it'll be dave.a*, etc. So the original code was perfectly fine. It worked absolutely fine. It proved itself in many Python attempts. But because of the way that we're using our matrix, we need to make a couple of minor adjustments. But let's go through the things that we don't need to change first. First of all, our node class is perfectly fine. As long as you've got a __eq___ method, then Python knows how to equate how two nodes are compared to each other. Okay, so if we have our eq statement just checking the positions, then if we say if node 1 equals node 2, it will actually just check whether the positions are the same, not anything else. And that's what we want. So that's what this code here means. Other than that, our parent is still one of our properties, and our position is a tuple and still one of our properties. And then a G, H, and F are part of our heuristic algorithm to actually give each cell in our grid a value. I'll explain that a little bit more in a few minutes. And then hash is just another function that creates a numerical representation of this node. Hashing is, for those of you who don't know, a process of taking something that's big and making a smaller numerical representation of it. For example, when you download a game on Steam, you'll notice that when it's installed, it will do a validation. It will validate the files, but it doesn't download all the files again and check that the two copies are the same. What it does is it creates a hash of each file, and it compares the hashes of the files against the ones that are stored on the Steam server. And they will be identical because the same algorithm is used to create a hash. In this case, all we've done is we've created a hash of position, which is another way of comparing two of our cells with each other. So that's what that does. That method just returns a hash of the position of this node. And because we will never have two nodes that have the same position, we know for a fact that this will be a unique number. So that's good. Into the a* method, the a* function, if you like, and we're still taking in a matrix, and we're taking in the start position and the end position. Now the end position will have been causing you problems, unless you solve this problem yourself, in which case well done. But the end position is problematic in the way that we use our matrix because of something that we'll discover as we get a bit further down. This tiebreaker number here is maybe not necessary, but I've put it in anyway just to make 100% sure that we don't get stuck with multiple paths and the algorithm just looping. Much like before, we've got our start node, which is just a node with no parent, and it is the start position, and we also have a node that we've created for the end position. We don't need to reset any values or anything, so you'll notice that the original algorithm we had set the F, G, and H, the G, H, and F values to 0, but they're already set to 0 up here in the init block, so we don't need to do that. Okay, then we have our open list and our close list, but now our close list is a set. A set is just a list type variable. We call them collections in programming. It just has some different functionality that we can make use of. We can exploit it for purposes of this algorithm. And just to be clear what's happening here, right, we have two lists. The closed list is a list of, for want of a better way of putting it, is a list of all of the cells that we've already checked, and we don't want our algorithm to go through and check them again. The open list is a list of cells that we have yet to check, that we want our algorithm to maybe check, but we haven't done so yet. When we start our algorithm, there's only one node in the open list, and it is our start node. We put the start node into the open list, and then that's ready to go. That list is ready to start being utilized, and the closed list will be empty at this point because we haven't put anything into it. What we're going to do then, this while loop here says while open list is greater than 0. In other words, while there is still stuff inside our open bag, we'll continue to loop through unless we find the node that we are looking for. Then what we'll do is we'll set our current nodes to be the first item in the open list, and we'll set our index to 0. And then what we're going to do is we're actually going to loop through the rest of the open list, and we're going to find the item which has the lowest F value. F is up here. This is the total of our heuristic algorithm that gives each cell a value. So if you're stood on the cell that the starting cell, your G, the G is the number of steps that you've taken, will be 0, but your H, which is the Manhattan distance, in other words, the distance across and up or across and down to the block that we're looking for, that's what the H value is. Okay. So what we're going to do is we're going to loop through the list of cells yet to be checked, and we're going to find the one with the lowest cost. So that's what this bit of code here does. Okay, that just makes sure that the cell that we're currently checking or doing all this extra checking against is the one that has the lowest heuristic algorithm cost. Then what we'll do is we'll remove the cell that we're currently looking at from the open list, and we're going to put it in the closed list, because once we've completed all the checks that we're about to check, we don't want to go back to the cell and check it again. We only want to check it once. Otherwise, we can get into all kinds of higgledy-piggledy. Then what we're going to do is we're going to double check. Is the node that we've currently got selected already the node that we're looking to go to? Are we already at our destination? If we are, then we're going to create a list, and we're going to take the current node and we're just going to save it in another value, and then we're going to check through. So we're going to say while current is not none, then we're going to add the position of the current node to a list, and then we're going to step backwards through the daisy chain to the parent of the node that we're currently in, and then we'll repeat the process. That's what this while statement is. We're just saying until we get to a node whose parent is none, in other words, the start and end nodes both have none. So our end node, the place where we're trying to get to, once we get to there, this loop will stop. Then all I'm doing is I'm removing the last item from that list, because the last item in the list is the position that we're already stood on. And then we're going to return that path in reverse so that we know where our thing, whatever it is that we're pathfinding for, will know where to go. That just returns an entire list of all of the cells that this thing needs to go through to get to where it needs to go. Now, this is going to run every single time we update the position of the objects, because the chances are, if these are enemy mobs, for example, they're going to want to walk towards the player. And you, being the player, will probably have moved in between each update. So we can't just run this algorithm once and expect our enemy mobs to find where we are, because it won't. So we have to actually run this every single frame. Now, that should not be a problem as long as we implement the code properly, which is where some of the errors that you might have encountered will come into this. So what we've done here, this is what happens. This code bit here is the code that will run when we get to the end node. But let's say we haven't found the end node. So what we need to do is create another empty list, and we'll call it children. So for the position or the node that we're currently standing in, we're going to check the positions above, below, to the left, and to the right. So we're going to loop through the 4 positions to the left, to the right, above, and below. And we're going to create a new node from each one of those new positions, like so. Only if the node is inside of our matrix, which is what this line checks. And this is one of the lines that you will have to make sure you get the order of business correct. So you need to make sure that node position 1 is greater than or equal to is not greater than or equal to the length of the matrix. So this is just going to check if it fits any of these 4 criteria, then we'll skip over it and go on to the next one. So we're checking off node position 1 against the length of the matrix, and we're checking that node position 0 and node position 1 are both not less than 0. So if it's less than 0, we'll continue. And we're checking node position 0 against length of the matrix 0. So we're actually checking, this is our x direction. That's what this bit is checking to make our x direction is correct. And this bit is checking our y direction, because if you remember, our matrix variable that we've passed is actually a y dominant matrix. So the first bracket is actually the y axis, and the second bracket is our x axis. Okay, so this line here, this whole bit of code here is just making sure that our current node's position, or rather the child node position that we're about to create, is actually inside the movable area. Then we're going to double check that there is actually a 0 there, because if it's not a 0, it's not a walkable space. So again, we will ignore it. However, this piece of code here is very, very, very important. If you do not put this bit of code in to this statement, your code will go into an infinite loop and it will crash. And I would be willing to bet that most people who've tried to implement this algorithm will have encountered this issue. The reason for it is that our player object is occupying a cell in the matrix. Our algorithm wants to find the path to the cell that the player is occupying. If we don't have this second piece here, what will happen is the algorithm, this piece of the algorithm, will tell our algorithm to ignore any cell which does not have a 0 in it, which means it will actually ignore the node that we're trying to get to, which means it will just go into an infinite loop trying to find a way of getting to a cell that it can't actually get to because the contents of that cell are not 0. So we need to make sure that node position is not equal to end node.position. If it is, then we're going to add our current node to the closed list, so we don't need to check it anymore. Okay, so there we go. Next thing we're going to do is we're going to create a new node like this, and we're going to append it to our children. And that's all this bit does. It goes through these 4 positions, and assuming that everything is okay, it's within the spaces of the matrix, and it's walkable, and it's not the end node position, then we'll add it to a list called children, which we created up here. Then what we're going to do is we're going to loop through every single one of our children, and we're going to check, is this already in the closed list? If it is, then we're going to do nothing with it. If it is not, then we will do the calculations for the heuristics. As you can see, we'll take the current node and we will add 1 to it in the G variable, so that we add 1 more step to the number of steps. Then we'll carry out this calculation here. It's a long one, but what we're doing is we're taking a floating point number. We're using absolute. Absolute converts negative numbers to positive numbers. It gives you the absolute value. So if our calculation of child node position minus end node position happens to be a negative number, it will convert it to a positive number, because remember that this is just the value of the cell in the heuristic algorithm. So we need this to be a positive number to be able to compare it with other cells. Otherwise, what we'll end up with is all of the negative cells will be considered to be lower value than the positive cells, and so it will always try to go in a negative direction, either X or Y, which will probably never get us to our destination unless the player is on the left or above. Okay, so the first piece of the calculation is child node position 0 minus end node position, the absolute value of that, and then we're adding to it child node position 1 minus end node position 1, again the absolute of that to make sure that it's positive, and then we're multiplying it by 1.0 plus a tiebreaker. So in this case, our tiebreaker is 0.02, so it'll be multiplying it by 1.02, which will give us a slightly different number. And then all our F value is child node G and H values added together. So that's how we calculate the cost of each cell relative to the destination. Then what we're going to do is we're going to go through our entire open list, and we're going to double check if our child node is equal to our open node, as in the node in the open list, and if the G value of our item in the child list is greater than or equal to the one that we've pulled out of the open list. So we're looping through our open list, open node, and we're just comparing the positions and the G variables. If the one that we're looking at is more expensive than the one that already exists in the open list, then we'll just ignore it and we'll move on. Otherwise, we're going to add our child node to the open list, which is where we'll loop all the way back to the beginning of our algorithm. And then we pull out the first item in the list, and then we grab our lowest F cost cell. So basically we just always go for the cheapest cell, because that's always going to be the nearest one to the destination. And then we will eventually make our way to the end node where this condition becomes true, and then we'll pull out this bit of code and it will run that instead. Okay, so I appreciate that may still be as clear as mud, but you've seen all of the code now. This definitely works. I've tested it to the nth degree. I've debugged it and run all kinds of well, I've extensively tested it, which is why this video is only about this algorithm. Because I want to make sure that you get this right, because if this doesn't work in your code, then basically your mobs are either going to crash the game or they're just going to sit there doing nothing. So it's very important that we get this all right. As always, members and patrons get access to the source code download, so they will have this file available to them. But you've seen all the code, so all you have to do is just make sure you make use of the pause function and copy the code correctly. And if you understand the code, you'll be able to make modifications where you see fit. So hopefully you found that useful, guys. Let me know what you think in the comments below as always, and I will see you in the next one. But until then, you take damn good care of yourselves, all right? Bye-bye.